Welcome to another deep dive. Today we're going really small, like down to the level of atoms, to explore the world of ferromagnetic thin films.
Wow.
These films are so thin, they're basically just a few layers of atoms.
Really thin.
And get this, their magnetic properties change drastically based on how many layers of atoms they have.
I can't wait to hear more about
We'll
this.
be looking at some fascinating research by Casio, Mazo Zuluaga, and Restrepo.
Okay.
They use computer simulations to explore how these films behave.
Simulations, that's interesting.
You ready to dive in?
Absolutely. I'm always fascinated by how such tiny changes can have such a huge impact on a material's behavior.
So the paper focuses on simulations using what's called the Monte Carlo method.
Yeah.
Can you break that down for us? Explain it in a way that won't make my head spin.
Let me see.
No pressure.
Okay, so imagine a 3D chessboard, right?
All right, I'm picturing it.
And each square on the board has a tiny little magnet that can point either up or down.
Okay, got it.
The Monte Carlo method is kind of like running a simulation where you let all these magnets randomly flip around and interact with their neighbors.
Like they're having a little magnet party.
Aha, yeah, kind of.
So by observing how these virtual magnets behave, researchers can learn a lot about how real magnetic materials work in the real world.
Exactly. It's like a virtual lab for magnets.
Oh, I like that, a virtual lab.
Yeah?
And in this case, the researchers simulated a structure called a simple cubic lattice,
Mm-hmm.
which I'm guessing is a very particular arrangement of atoms,
You got it. It's a very organized and structured arrangement.
which I'm assuming makes it easier to study the fundamental physics at play.
Exactly.
Okay, so we've got our virtual lab set up, our simple cubic lattice,
Right.
and they were specifically looking at how the magnetism of these thin films changes based on how many layers of atoms they have.
Precisely.
Which they measured in what are called monolayers,
Yep.
which essentially means like a single layer of atoms.
Yeah, one atom thick.
They also played around with the size of the film's base, right?
They did.
But always keeping it a square shape.
Yes. Always a square.
So I'm picturing this like microscopic magnetic checkerboard, and we're adding or removing layers to see how it behaves.
That's a great way to visualize it.
What were some of the key things they observed?
Well, one of the first things they noticed, kind of like what you'd expect,
Yeah.
is that as you heat up these films, their magnetization decreases.
So like the hotter it gets, the weaker the magnet.
Yeah, you can think of it that way.
Makes sense. Because heat generally makes things more chaotic, right?
It does. Heat things up and the atoms start jiggling around more, and that causes their magnetic alignments to break down.
Right, right. So it's like the heat is disrupting their magnetic harmony.
Exactly.
But I have a feeling there's more to it than that.
Oh, there's definitely more to it.
Did they find anything unique about how the magnetization changes with temperature? Especially in these super thin films.
You hit the nail on the head. It's not that simple. You see, the temperature at which the film completely loses its magnetism.
Which we call the Curie temperature, or TC for short.
Exactly, the Curie temperature.
So what about it?
It actually changes depending on how thick the film is.
Oh, really? So the thickness of the film affects the Curie temperature?
Yep.
That's interesting. So thinner films lose their magnetism at lower temperatures compared to thicker films.
Exactly.
I would have thought it'd be the other way around.
Yeah, a lot of people think that,
You'd think a thicker film with more magnets would be stronger,
right, you'd think more magnets, stronger magnet.
and therefore it would take more heat to make it lose its magnetism.
Yeah, but it's not just about the total number of magnets.
Oh, okay, so what else is going on here?
It also has to do with how these magnets or atoms are interacting with each other.
Okay.
And what's really cool about these simulations
Yeah.
is that the researchers could actually see
What?
how the atoms at the surface of the film,
Oh, at the very edge.
yeah, right at the edge,
Okay.
heaved differently compared to the atoms in the interior, which we call the bulk.
So the location of the atom within the film affects its behavior.
Yeah, think of it like
Like what?
being at a crowded concert, you know?
All right. Yeah, I can picture that.
If you're in the middle of the crowd, you're surrounded by people bumping into them constantly, right?
Yeah, I can't really move much.
But if you're at the edge, near the outskirts of the crowd,
You've got more space to groove.
exactly, you got more room to move around.
So are you saying the atoms at the surface are like the edge of the crowd dancers, magnetically speaking?
Yes, they have more freedom because they have fewer neighboring atoms to interact with.
Interesting. So they're not as constrained.
Right, their magnetic behavior is a bit different compared to those stuck in the mosh pit of the bulk.
So this difference between the surface atoms and the bulk atoms,
Yeah.
this plays a role in what the researchers call a dimensional shift.
Exactly, it's all connected.
Okay, hold on. Dimensional shift.
Yep.
Are we talking science fiction here?
Not quite.
How can a material change its dimension?
It's not about the film physically changing its dimension.
Okay,
It's more about how it behaves magnetically.
gotcha.
So very thin films, those with just a few layers of atoms, they act more like a two-dimensional system.
Like they're confined to a flat plane.
Exactly. As if they're stuck on a flat surface.
Okay, I'm kind of visualizing that, a flat sheet of magnets.
Right.
And what about the thicker films? What happens as we start adding more layers?
Well, as you add more layers, things get interesting.
Okay, I'm listening.
The films start to behave more like a three-dimensional system.
Ah, so they break free from their flatland prison.
Haha, yeah. The atoms have more freedom to interact in all directions.
So they're not just confined to that flat plane anymore.
Right.
And this shift, this transition from 2D to 3D behavior,
Yeah,
that's reflected in how the Curie temperature changes with thickness.
exactly. It all ties together.
So just by changing the thickness by a few atoms, we can drastically alter the magnetic properties of the material.
That's the amazing part.
That's pretty incredible. What else did they find out about these dimensional shifts?
Well, they actually went a step further and compared their simulation results
Okay.
to theoretical models.
All right.
And they found something pretty cool.
What's that?
For those really thin films, the ones acting like 2D systems,
Yeah.
the Curie temperature they got from their simulations
Hmm.
matched up almost perfectly with what you'd expect
Yeah.
from a 2D Ising model.
A 2D Ising model, refresh my memory on that one.
It's a theoretical model
Right.
that's often used to study magnetism, specifically in 2D systems.
Ah, okay, so it's like a theoretical framework for understanding how magnets behaved in 2 dimensions.
Exactly.
So their simulations for these super thin films lined up with what theory predicted for a 2D system.
Yep, pretty neat, huh?
Yeah, that's pretty solid evidence to support their claims of this dimensional shift.
It is.
What happened as they started making the films thicker?
Good question.
Did they see things start to deviate from this 2D behavior?
They did.
Tell me more.
As they simulated thicker films, the Curie temperature, it started to increase.
It went up.
Yeah, and it moved closer to the values
Values for what?
predicted by a 3D Ising model.
Ah, I see. So as they added more layers, the film's behavior started to shift away from that 2D model.
Exactly. It was like they were watching the films transition
Transition from what?
from acting like a flat plane, a 2D system,
Yeah.
to acting more like a bulk 3D material.
So it's like the film was gaining another dimension.
You could say that.
That's fascinating. So the Curie temperature was almost like a fingerprint
Okay.
for the effective dimension of the film.
I like that, a fingerprint.
That's a really neat way to visualize it.
Yeah.
Now, earlier you mentioned something about critical exponents.
Right.
Can you remind me what those are again?
Sure.
And maybe explain how they fit into this whole picture.
Okay, so critical exponents, well, they're basically mathematical tools
Okay.
that we use to describe how a material behaves
Behaves how?
near a critical point.
Like the Curie temperature.
Exactly. Like the Curie temperature. They
Yeah.
give us deeper insights
Deeper insights into what?
into the finer details of the transition
Transition from what to what?
from a magnetic state to a non-magnetic state.
So like how the material loses its magnetism.
Exactly. But on a whole granular level.
Okay, I'm intrigued.
So in this study, the researchers,
Yeah.
well, they calculated 3 specific critical exponents
Okay.
that describe how magnetization, susceptibility,
Acceptability, what's that?
and correlation length.
And correlation length. Okay, we're going to need some definitions here.
You're right. Sorry.
No worries, just trying to keep up.
So susceptibility, basically, it refers to
Refers to what?
how easily a material's magnetization changes
Changes in response to what?
in response to an external magnetic field.
Okay, so like if you bring a magnet close to it,
Yeah. Imagine that.
how much does its own magnetization change?
That's susceptibility.
Got it. So high susceptibility
Means what?
means it's very responsive to an outside magnet.
Yes. Its magnetization will, quickly align with that external field.
Interesting. And what about correlation length?
Right. So correlation length, think of it as a measure of dissonance
Distance between what?
between atoms within the material.
Okay.
And it tells us how far apart those atoms need to be
Okay.
before their magnetic orientations become, uncorrelated.
Uncorrelated.
Meaning they're no longer aligned.
So it's like if two atoms are within this correlation length, they're basically on the same magnetic page.
You got it. But if they're farther apart than the correlation length,
Yeah.
they're kind of doing their own thing, magnetically speaking.
Ah, so it gives us an idea of the size of those magnetic domains.
Exactly. Those little regions where the atoms are all aligned.
Okay, so we've got susceptibility telling us how responsive the film is to an outside magnet, and correlation length giving us a sense of the size of those magnetically aligned regions.
It's all about how the spins are interacting.
So what did they find out about these critical exponents? Did anything stand out?
Well, their simulations suggested something pretty interesting.
What's that?
Those critical exponents, they actually shifted as the film thickness changed.
Really? So the exponents themselves were changing?
It seems so. It's like the very nature of the transition.
You mean the way the material goes from magnetic to non-magnetic?
Yeah, exactly.
Okay.
Is being affected by the film's thickness.
Wow, so we've got the Curie temperature shifting,
right?
surface atoms acting differently,
Uh-huh.
and now even these critical exponents changing with thickness.
It gets pretty complex.
It's like every time we add another layer of atoms, the whole system gets more and more intricate.
It really highlights how complex these materials are,
Yeah.
even though they seem so simple at first glance.
Right.
And it also shows the power of simulations.
How so?
Yeah. We can actually tweak things at the atomic level in these simulations.
Like playing with atomic building blocks.
Uh-huh, yeah. And we can see how those tiny changes
Yeah.
ripple through the entire system.
It's mind-blowing to think we're starting to have that level of control over materials.
It is.
But let's shift gears for a bit.
Okay.
We've been talking a lot about theory.
Right.
What about the real world?
Good point.
You mentioned before that all of this has some pretty big implications.
It does.
For things like data storage, sensors, even this futuristic-sounding field of spintromics.
Yep, all of that.
Can you expand on that a bit?
Absolutely. Let's start with data storage.
Okay.
Our devices are like constantly demanding more and more storage.
It's true, always needing more space for photos, videos, apps.
Yeah, all of that.
So how could these thin films help us?
Well, think about hard drives.
Okay.
If we can use these ferromagnetic thin films,
Mm-hmm.
we could potentially create hard drives.
Why?
Smaller, faster, and more energy efficient.
Really, all that from just using a different material.
Potentially. See, thinner films actually require less energy
Less energy for what?
to switch their magnetic state.
Oh, okay.
And that switching, that's how we write data.
Ah, I see. So by using thinner films, we could create hard drives that need less power to operate.
Exactly.
That makes a lot of sense. What about the sensor applications?
Okay, yeah, so,
How could we use these films to make better sensors?
well, these films are super sensitive
Super sensitive to what?
to changes in magnetic fields,
Okay.
which makes them perfect for sensing applications.
Can you give me an example?
Sure, imagine like a medical sensor
Okay.
that could detect really subtle changes
Changes in what?
in the body's magnetic fields,
Interesting.
potentially leading to earlier disease detection,
Wow, that would be incredible.
right?
Or how about environmental sensors?
That's another great application.
Could they use these films
They could,
to provide really accurate readings?
of things like pollution levels
Yeah.
or other important environmental factors.
Those are some really interesting applications. Now, I'm still a bit unclear about spintronics.
Yeah, spintronics is a bit more out there.
Can you give me like a quick crash course on what it's all about?
Okay, so spintronics,
Yeah.
it goes beyond just using the electron's charge.
Okay.
It also utilizes its spin.
Spin. What's spin?
Think of it like a tiny magnetic moment.
A tiny magnetic moment.
Yeah, that's associated with each electron.
So every electron is like a mini magnet,
You got it. And spintronics is all about controlling that spin.
controlling the spin of electrons.
Yep, to create new types of electronic devices.
So instead of just thinking about electrons as tiny balls of charge,
Mm-hmm.
we're also considering their magnetic properties.
Exactly.
Fascinating. And how do these thin films fit into all of this?
Well, they're crucial in spintronics because you can be used
Used for what?
to create and control what we call spin currents.
Spin currents. What are those?
They're flows of electrons, but
But what?
with their spins aligned.
Ah, so it's like a stream of many magnets all pointing in the same direction.
Yep, you got it. And being able to manipulate those spin currents
Yeah.
opens up a whole world of possibilities for new types of electronics.
It sounds like we're on the verge of some major breakthroughs in electronics.
It's definitely an exciting field.
But before we get too carried away, let's just take a moment to recap what we've learned so far.
Good idea.
We started by exploring how the properties of these ferromagnetic thin films
Mm-hmm.
change so much depending on their thickness,
Right.
which led us to that really cool concept of a dimensional shift,
Yeah, those dimensional shifts are wild.
where thin films act like 2D systems,
Yep.
and thicker films start behaving more like 3D systems.
It's like they're transitioning between dimensions.
And we saw how the Curie temperature and those critical exponents
Yeah.
provide really valuable clues about those changes.
They do.
And then we touched on all the potential real-world applications.
Right, like data storage, sensors, spintronic.
It seems like these thin films could revolutionize so many fields.
The potential is huge.
But I feel like there's still more to uncover.
There's always more to explore.
What else is there to learn about these remarkable materials?
Yeah, there's always more.
It's been quite a journey exploring these ferromagnetic thin films.
It has.
I mean, it's clear that these materials have so much potential
That's definite.
to revolutionize all sorts of fields.
Exciting.
But I'm curious, the research we've talked about
Mm-hmm.
focused on a simple cubic lattice structure, right?
It did.
What if we start exploring other arrangements of atoms?
Ah, that's a great question.
Could we, like, unlock even more unique magnetic behaviors?
Absolutely. The arrangement of atoms within the film,
Yeah.
well, it plays a huge role in determining its properties.
Right. It's like the architecture of the
Oh,
materials.
yeah,
A simple cubic lattice. It's a great starting point.
it is.
But it's just one of many possibilities, right?
There's so many others.
Imagine exploring more complex lattice structures.
Yeah.
Or even combining different materials together.
You could create entirely new magnetic composites.
Like we're building with atomic Legos.
Haha. That's a great way to think about it.
Creating materials with these, like, tailor-made properties.
It's the future of materials science.
But with all this amazing potential, I mean,
Yeah,
are there any downsides?
of course.
Any challenges we need to think about with these thin films?
Definitely, there are always challenges.
Like what?
Well, one of the biggest ones is fabrication.
Fabrication. What do you mean by that?
Actually creating these thin films,
Yeah.
but with atomic precision.
Ah, so it's not as easy as just, like, stacking atoms like building blocks.
It's way more complex than that.
Okay, so what's involved?
It requires these very specialized techniques
Okay,
and equipment.
got it.
It's not just about stacking atoms.
Yeah.
It's about controlling their growth
Mm,
and arrangement
at such a tiny scale.
at the nanoscale.
So it's a very delicate process.
Oh, it is.
And what about their stability?
Good point.
I mean, these films are incredibly thin, right?
A few atoms thin.
Just a few atoms. How do we make sure they don't, like, fall apart when we actually try to use them?
That's a major concern.
Okay.
Durability and stability are super important.
Right.
I mean, these films are delicate.
Yeah.
So researchers are constantly working on ways to protect them.
Like what? What can they do?
Well, some things they're exploring
Yeah.
are things like encapsulating them
Encapsulating them in what?
in other materials.
Ah, so like giving them a protective coating
Yeah, you could think of it like that, or
Yeah.
developing new fabrication methods.
to make them more robust.
Exactly.
So there's still a lot of work to be done
There's always more to do.
to make sure these thin films can actually be used in real-world devices.
But the progress is really exciting.
It is. This whole deep dive has been fascinating.
I agree.
It really shows how much potential there is
Yeah.
when we start manipulating materials at the atomic level.
It's a whole new world down there.
It really makes you wonder what other groundbreaking discoveries are waiting for us at the nanoscale.
Who knows what we'll find next?
It's incredible to think that the smallest of things
Yeah.
can lead to such huge advances in technology.
It's mind-blowing.
So, to our listeners out there, stay curious
Keep asking questions.
and never stop exploring the world around you.
You never know what you might discover.
Perhaps one of you listening will be the one to unlock the next big breakthrough in the thin film technology.
That would be amazing.
It's been a pleasure diving into the world of ferromagnetic thin films with you.
Likewise.
Thanks for joining us on this deep dive.
Until next time.
Keep those minds engaged.
And keep exploring.
The wonders of science.
Yeah, I know them are.